In this lesson, we're going to talk about what's called the fundamental theorem of calculus. And this fundamental theorem of calculus has two parts to it. I'm actually going to go out of order than what the book shows us because I feel like if we go over part 2 first, it'll make it a little bit easier for you to understand the first part. And then the other thing that I want to point out, that I really want to stress for this section, is that in the previous sections, when we evaluated a definite integral, we only have talked about two methods so far to do that. We've talked about using the definition of the definite integral, which was a fairly lengthy process, using the limit as n approached infinity of the Riemann sums. And then that was fairly lengthy. And then the other method that we used was using geometric formulas if the shape that we were trying to find of that area under the curve was a simple basic shape that we had a formula for, such as a circle or a triangle or a rectangle. Now, most of our functions do not have that kind of a simple shape that will make it easy for us to just use a geometric formula. So most of the time that isn't going to work. And we really don't want to have to use the definition every time because that's fairly lengthy. So what the fundamental theorem of calculus does is it gives us a shortcut. So it gives us a much easier way to handle evaluating integrals. So in the second part of the fundamental theorem of calculus, what this basically says is if we want to evaluate an integral from a to b using our limits, our lower limit is a and our upper limit is b, and we're using a function f of x, the f of x has to be continuous over that interval from a to b for this to work. And then what happens is we find the antiderivative for that function and we evaluate it at the upper limit, we evaluate it at the lower limit, and then we find the difference. Now, because this is subtraction, the order matters. You always want to evaluate your function, your capital F function, at b first, and then at a, and subtract. So you always take capital F of b minus capital F of a. You do the upper limit first. So this has always got to be the upper limit first, because the order matters. Okay, so let's go ahead and use this fundamental theorem of calculus to evaluate this integral. So we have an integral from -2 to 2 of t squared minus 4. Now, when we look at the graph of t squared minus 4, it's a nice simple graph that we're familiar with. It's just a quadratic. It's concave up because the leading coefficient is positive. My x-intercepts are at -2 to 2. Those are my zeros. And then my y-intercept is going to be at -4. Now, this integral is asking me to find the area between the curve and the x-axis on the interval from -2 to 2. So this integral is asking us to find this area here. Now, this doesn't have a simple geometric shape that we have a formula for, and we really don't want to have to use the definition if we don't have to because that's a lengthy process. So this is a perfect example of when we can use the fundamental theorem of calculus. So to evaluate this integral using the fundamental theorem of calculus, basically all we're going to do is find the antiderivative and then evaluate it at 2, evaluate it at -2, and then subtract both of those. So we're going to take capital F of 2 and then subtract capital F of -2. So to find the antiderivative, remember the properties of integrals tells us that we can take the integral or the antiderivative of each term separately. So I'm going to find the antiderivative of t squared. So thinking backwards, now we have the derivative and we're trying to find the antiderivative, that original function. So I have to think backwards, and I'm going to add 1 to the exponent and divide by that exponent. And then to find the antiderivative for -4, that's going to be -4t. and then I have to add in my constant. So I have my family of functions here that will work. If I take the derivative of this now, this is considered my capital F. So if I take the derivative of this capital F of t, I'll get t squared minus 4. Now I want to evaluate this on the interval from -2 to 2. This is the notation, and you might not have seen this before. This is the notation you use for evaluating it on an interval. You put your upper limit at the top, the lower limit at the bottom, and you just put a line, a vertical line in between the two. So this is telling me to plug in 2 first. So I'm going to make a note here. Plug in 2 first. That's your upper limit. So I'm going to take 2 and plug it into my antiderivative. So I have 2 to the third over 3 minus 4 times 2 plus c. So this is my capital F of 2. Now I'm going to subtract my capital F of -2. That's my second limit, my lower limit. Plug this in second. Okay, so I'm going to plug in -2 to the third over 3 minus 4 times -2. Then I have my plus c. So now I'm going to take 2 to the third divided by 3. That gives me 8 over 3 minus 8 plus my constant. Then I'm going to subtract everything that's in these parentheses. I get -2 to the third gives me -8, so that gives me -8 thirds plus 8 plus c. Now I'm going to subtract everything that's in those brackets. So I have 8 thirds minus a -8 thirds. So that's going to give me a positive 16 thirds. Then I take -8 and I subtract an 8. That's going to give me a -16. And then I have this constant minus this constant. Those two disappear. And then what I'm left with, once I simplify this, I'm going to get -32 over 3. So whatever units this is supposed to be in, if this was in the context of a problem, we want to make sure, since this represents area, it's going to be units squared. Now, remember I said anything that's below the x-axis is considered a negative area. It doesn't mean that the area itself is negative, it's just indicating the location of the area. So if you notice, this area is below the x-axis, and that's why it came out to be negative. So just keep that in mind, that the area isn't necessarily negative, it just indicates the location of the area. For this example, we're going to do the same thing. We're going to use the fundamental theorem of calculus to evaluate this interval. We do have to simplify a little bit before we actually integrate, though. It will make it a lot easier. So we have the integral from 1 to 9 of x minus 1 over the square root of x dx. First, what I'm going to do is I'm going to rewrite the square root of x as x to the 1/2. Now I'm going to take that x to the 1/2 and divide it into the x into the -1. And I'm going to split up those fractions and simplify. So I have x over x to the 1/2 minus 1 over x to the 1/2 dx. Now I'm going to simplify. If I have x over x to the 1/2, when I divide and I have the same base, I subtract my exponents. So this is going to give me an x to the 1/2. And for the 1 over x to the 1/2, I'm just going to rewrite that by taking the reciprocal and writing the exponent with a negative. I personally think this will make it easier when we work backwards to find the antiderivative. So now let's find the antiderivative. If I take the antiderivative of x to the 1/2 using the power rule and working backwards, I'm going to add 1 to the 1/2 to that exponent, and that gives me x to the 3/2, but I have to divide by the 3/2. I'm going to do the same thing with x to the negative 1/2. If I add 1 to the exponent, that's going to give me a positive 1/2, and then I have to divide by the exponent. And then, of course, I have plus c, my constant. And I have to evaluate that from 1 to 9. To make it easier when I evaluate, instead of having a complex fraction, I'm going to do a flip and multiply. So I'm going to rewrite this as 2/3 x to the 3/2 minus 2x to the 1/2 plus c, and I'm going to evaluate this from 1 to 9. So the first thing I need to do, this is my capital F function, and I'm going to evaluate it at the upper limit first at 9. So I'm going to find f of 9 first. When I plug in 9, I get 2/3 times 9 to the 3/2 minus 2 times 9 to the 1/2 plus my constant. So that's my f of 9, my capital F of 9, and I'm going to subtract my capital F of 1. So when I plug in 1, I get 2/3, 1 to the 3/2 minus 2 times 1 to the 1/2 plus c. Now when I finish this, what's going to happen is my c's disappear. I get my constant minus this constant, that disappears. When I multiply this, I get 18 and minus 6. And I'm going to subtract everything that's inside the brackets. So I have 2/3 minus 2. Now I have 18 minus 6 minus 2/3 plus 2. When I add that all up, I'm going to get 40/3. When I look at the graph of this picture, x minus 1 over the square root of x on the interval from 1 to 9 looks something like this, just a sketch. So this is the area we found. And so that makes sense that we got a positive value. So that area that I highlighted in pink is equal to 40/3 in terms of area. And remember, since this is area, we would have whatever the units are, and then we would square it. So in this example, we're going to go through an application of integration. And the problem reads that there's 2 people, James and Kathy, and they're racing on roller skates. They're going to race along a straight track, and whoever has gone the farthest in 5 seconds wins a prize. If James can skate at a velocity of f of t, which is 5 plus 2t feet per second, and Kathy can skate at a velocity of g of t is equal to 10 plus cosine pi over 2t feet per second, who is going to win the race? So basically what we need to do here is find who has skated the longest distance in that time interval from 0 to 5 seconds. So if you think back when we were learning about derivatives, we learned that if we had a position function that gave us the position of some moving particle, whatever that is, along a path, and we plugged in a value of t, it gave us the position of that particle. And then we found out if we took the derivative of that position function, we got the velocity. Well, now we need to find the position, and we're given the velocity, so we're going to work backwards and find the antiderivative, which means we're going to have to integrate. And we want to do this on an interval from 0 to 5 seconds to find the total distance traveled. So we're going to integrate both of these functions that represent the velocities for James and Kathy, and then we're going to use that and integrate over the interval from 0 to 5 and see who's traveled the farthest. So for James, we're going to integrate from 0 to 5, 5 plus 2t dt. When I find the antiderivative of 5, that gives me 5t. When I find the antiderivative of 2t, I get 2t squared over 2, and I can get rid of those 2's. And I have plus c, and I want to evaluate that from 0 to 5. Now that we've done a couple of examples of integration using the fundamental theorem of calculus, we can see that when I subtract and I evaluate this on the integral from 0 to 5, that constant is always going to disappear. So now that we are familiar with that, we don't have to put that c in there anymore because we know it's going to drop out anyways. You can put it in if you'd like, but I'm going to start dropping that off since we know what happens to that c anyways. So I'm going to plug in 5, and I'm going to get 5 times 5 plus 5 squared minus, now I'm going to plug in 0, 5 times 0 plus 0 squared. This is my big F of 5, and I'm going to subtract my big F of 0. When I do that, I'm going to get 50. Now let's do this for, who's the other person? Kathy. So I'm going to integrate on the interval from 0 to 5, 10 plus cosine of pi over 2t dt. Now when I integrate 10 and I find the antiderivative and work backwards, that's going to give me 10t. When I find the antiderivative of cosine, that's going to give me sine of pi over 2t. But keep in mind, if we were taking the derivative, we have to multiply by the derivative of the inner function. So working backwards, I have to divide by the derivative of the inner function. So I'm going to have 2 over pi here in front, because if I divide by pi over 2 and I do a flip and multiply, really I'm multiplying by 2 over pi. Okay, now I'm going to evaluate that from 0 to 5. So when I plug in 5, I'm going to get 10 times 5 plus 2 over pi times sine of pi over 2 times 5. Now I'm going to subtract. So this is my big F of 5. I'm going to subtract my F of 0. That's going to give me 10 times 0 plus 2 pi times the sine of pi over 2 times 0. Now, when I clean that all up and I put that in my calculator, remember to be in radians, I'm going to get approximately 50.6. So remember what this means. This is the total distance traveled. So for James up here, and this is my fault, I forgot to put the units in, and I should have. James traveled a total of 50 feet, where Kathy traveled a total of 50.6 feet. So it looks like Kathy won this race because she went just a little bit farther than James, but not by a whole lot. Now the units for this is going to be feet, because if we think about what we're finding the area of, if I draw a graph of the velocity, I'm just going to draw some generic graph. This is the velocity, and we want to find the area under the curve of the velocity. That's this area here. On the y-axis, we have the velocity. On the x-axis, we have time. So when we find the area under the curve, we're taking the velocity times the time. And in this case, the velocity is feet per second. And when I multiply it by the number of seconds, the seconds cancel and I'm left with feet. So now let's talk about the fundamental theorem of calculus part 1. This theorem states that if f of x is continuous, and this is a key component, if f of x is continuous over an interval a to b, and is closed interval a to b, And the function capital F of x is defined by the interval from a to x of f of t dt. If this is true for every x on that interval ab, then the derivative of capital F is equal to lowercase f on that interval a to b. So let's say we have some generic function. I'll call it f of t. And we're looking at an interval, a closed interval a to b. And we pick just some random x between a and b on that interval. So let's say this is x. Now, the fundamental theorem of calculus tells us that if f is continuous over this interval, then capital F of x is differentiable at every x, any x that I pick on that interval a to b, and the derivative of capital F of x is going to be equal to the lowercase f of x. Let's connect this idea to the second part of the fundamental theorem of calculus, which we started to look at. If I pick two other values on the interval from a to b, let's say c and d. Now, if I wanted to evaluate f of d minus f of c, let's think about what that means. Using this fundamental theorem of calculus, if I take capital F of d, that means everywhere I see x in that statement, I'm going to replace it with d. So I have that capital F of d is going to be the integral from a to d of f of t dt. Now I'm going to subtract capital F of c and do the same thing. Everywhere I see x in that statement, I'm going to plug in c. So I have the integral from a to c of f of t dt. Now, let's think about what this means, and I'm going to color code this to make it easy to see this. This statement here, this integral from a to d of the function f of t means we're looking at the area under the graph between a and d. So between a and d, that's this area here. Now, this integral tells us we're looking at the area under the curve f of t between a and c. So I'm going to do that in green. So that's this area here. So if I take that entire pink area and I subtract off the green area, what I'm left with is just this area here that I'm highlighting in yellow, the area between C and D. So if I rewrite the statement using integral notation, if I want the area under the curve of f of t on the interval from C to D, then I'm going to write it like this. So what we just showed was that capital F of D minus capital F of C is given by that integral using the limits from C to D of f of t dt. And that's what we have been using so far to calculate our definite integrals. So what this tells us is that if this is true, then the derivative of capital F is going to be equal to f of x over that interval AB. So now that we've gone through both parts of the fundamental theorem of calculus and we've connected the concept between the two, let's go ahead and work through this example using the fundamental theorem of calculus. Now it says we're going to find the derivative of this function g of x that's defined as an integral. So the fundamental theorem of calculus says if I have a function that's defined using an integral from the lower limit a to an upper limit x, and a is some constant, and the function that we're integrating is f of t, if this function is continuous on the interval in which you're trying to integrate over from a to x, then we can say that the derivative of that function is just f of t when it's over that interval from a to x. So if we look at this example that's given to us as g of x, we have to first make sure that that function is continuous between 0 and x. Now, the only place that I'm concerned about this function 1 over t cubed plus 1 being undefined is at x equals -1. And since we're on the interval from 0 to x, we're already past and above -1. We're going from 0 and above. So I'm not worried about having any issues of continuity on the interval from 0 and up. So I can use the fundamental theorem of calculus here, and I can say, well, the derivative of g of x must be 1 over x to the third plus 1. In this next example, we're going to use the fundamental theorem of calculus with the chain rule. If you notice, we have the function capital F of x is equal to the integral of sine t of dt. And we need to find the derivative of capital F. So we don't just have x up here. To use the fundamental theorem of calculus, we need that upper limit to be x. And so we can look at capital F of x as a composition function. So think of f of x as a composition function of h of g of x, where h of x is equal to the integral from 1 to x of sine t dt, and g of x is the square root of x. So when I find h of g of x, that means I'm going to take the square root of x and plug it in everywhere I see x. So what this tells me is now, if I have f of x as a composition function, then when I take the derivative of f, I'm going to take the derivative of h, evaluated at g of x, but I have to remember to multiply by the derivative of g, which is that inner function, the square root of x. So when I take the derivative here of capital F, I'm going to take the derivative of my outer function, which is the integral from 1 to x sine t of dt, but it's going to be evaluated at g of x. So that's going to give me sine square root of x. But now I have to multiply it by the derivative of that inner function. The derivative of that inner function is going to be 1/2 x to the -1/2, because we can rewrite the square root of x as x to the 1/2 and use the power rule. So now when we clean this up, I have the sine of the square root of x all over 2 times the square root of x in the denominator. So this is the derivative of our capital F function using the fundamental theorem of calculus and the chain. Okay, in the last example, we're going to use the fundamental theorem of calculus, and we're going to be dealing with two variable limits of integration. So we have this function, capital F of x, is equal to, and is defined by an integral from x to 2x, t to the third dt. And we have to find the derivative of this function. So in order to use the fundamental theorem of calculus, we have to have a constant as the lower limit and then x as the upper limit. So we're going to have to rewrite this function in a way that we can use the fundamental theorem of calculus. So I'm going to first start off by rewriting x to the 2x of t to the third dt as two integrals. And so if you imagine just some generic function, and we have a lower limit of x, an upper limit of 2x, Now, I don't know for sure that 2x is bigger than x because it just depends on what value you plug in for x. But for the sake of visualizing what's going on here, I'm going to make that assumption that 2x is bigger. And so I'm going to imagine that there's some constant somewhere in between here. If I take, using my properties of integrals, if I take the integral from x to 2x, I can split it up into two integrals. The integral from x to c, and then the integral from c to 2x. So that's exactly what I'm going to do here. So I'm going to go from x to some constant c of t to the third dt, and I'm going to add that to the integral of c to 2x, t to the third dt. Notice that in this first integral, my constant is in the upper limit and my x is in the lower limit. In order to use the fundamental theorem of calculus, those need to be swapped. I need to have my constant as the lower limit and my x as the upper limit. So if you think back to our properties of integrals, I can switch those limits if I switch the sign of the integral. So now I'm going to rewrite this integral as a negative integral from c to x. So I switched my limits and I switched the sign of the integral of t to the third dt plus c to 2x t to the third dt. Now this integral here, like the previous example, we do not have x as the upper limit. So we're going to think of this as a composition function where 2x is that inner function. So I'm going to take the derivative of this integral, evaluate it at 2x, but I have to remember to multiply by the derivative of 2x. So when I finish writing this down, when I take the derivative of this integral, I'm going to get negative x to the third plus, now when I take the derivative of the second integral, this is going to be 2x to the third times the derivative of 2x, which is 2. So this is going to give me negative x to the third plus 8x to the third times 2, which is 16x to the third. And when I combine my like terms, I get 15x to the third. So this is my derivative of f, and that's using the fundamental theorem of calculus. That's using the chain rule, and then we also had to use some properties of the integrals to rearrange the expression in a way that we can use the fundamental theorem of calculus.